In section 2.3, we're going to modify something that we've already taken a look at before, which is the harmonic oscillator. And a harmonic oscillator that we saw before was something that we called undamped, or another word for it is unforced. And by damped, really what we're saying is with friction. So an undamped harmonic oscillator is something that if you were to set it in motion, kind of push the spring in or pull the mass out and release it, it would just kind of wobble back and forth forever. But now what we're going to do is add friction to it. But just a quick reminder, we've got our spring attached to some fixed point over here. And this is a spring with a known constant. And that spring constant tells us kind of how stiff the spring is. And we have some set fixed rest position over here. And specifically we call that y equals 0. We're going to use y as our variable for position. And so the mass gets attached to that spring, and we can either move it towards or away from the fixed point. And by sliding the mass towards the fixed point like this, kind of moving it along the table towards the fixed point, we are moving it in the negative y direction. And this is what we would call a compressed spring. And so the force that would be applied by the spring, because it's compressed, the force is going to try to push in the opposite direction. So the restorative force is going to push in that direction. And that might be, if we let go at that point, if there's no friction, that would be the only force acting on the mass, is that restorative force of the spring. But we can just as easily kind of slide the mass in the opposite direction, which is in the positive y direction. And that's what it means to stretch the spring. And in this case, the restorative force is going to be the spring kind of pulling backwards on it this way. So just as a context, this is kind of where we were before. And we saw how we could use Newton's law and Hooke's law and a little bit of manipulation, algebraic manipulation. We found out that we have a second order differential equation. If you remember, Hooke's law was force, the restorative force was equal to negative k times y. And Newton's law, if you remember that one, that was just the net force is equal to its mass times its acceleration. Whatever the object is, that's always the case. The net force on an object is equal to whatever its mass is times its acceleration. Now, this is specifically true for situations where we have a changing position. The further you go in physics, the more you realize this is actually also true for changing mass. We're not going to get into that in this course, but it's possible to rewrite this equation as not just a change in position, an acceleration, but also a change in mass. So you can modify that equation as needed. But for our purposes, we're going to take this second order differential equation. This is a second order. And we can, with a little bit of modification, recognize that the first derivative of position is velocity. And so we can rewrite this equation up here in terms of velocity and position. And you wind up with an equivalent first order system. And it turns out that these two things are 100% equivalent to each other. And the other thing that we did was kind of a cheat, but it's just to make things easy for ourselves. We said, let k and m be the same size, and so that k over m is just 1. And that's just for simplification purposes. We didn't have to, but it makes it a little bit easier to manipulate. And of course, we can use Maple to see what that looks like, to actually sketch the y versus t graph. And we've seen that once before, so I'm not going to show it in this video. You can check that out at the 2.1 video, part 2, and how that looks, and what it looks like to have a initial position on the phase plane of y0 of 1 and v0 of 1. That means the initial position is stretched 1 unit, right? Whatever the unit happens to be for position. And it's positive, so that means we're stretching. And then, of course, the v value, the initial velocity, is telling us the initial velocity is moving in the positive direction. One unit of velocity, which is, remember, distance over time. So that information allows us to see a phase plane graph that when we sketch this thing, we see y versus v. We see a circle, and I'm going to try really hard to draw a circle. It's very difficult to do. I should always draw the circle first and then put in the axes later. It's a little bit easier to do it that way. But this would correspond to the initial position of 1, 0. This would correspond to the position of 0, 1. And if you have a particular circle that has an initial condition right here of 1, 1, then notice that would no longer be 1 unit out. That's a little bit more, and that's a little bit more. But if this is 1, 1, you're going to see it move. This particular thing would move. And you can kind of estimate what direction is it going to move. Is this on the phase plane going to move this way, or is it going to move this way? Is it going to move clockwise or counterclockwise? Well, you can ask yourself, if you started with a positive position, the restorative force is going to want to make you go that direction. And the restorative force is going to want to slow down your velocity, right? So a positive velocity means that you're moving in this direction. And so the direction on the phase plane of this curve is going to be in the clockwise direction, because from this point it would start to continue moving with a positive velocity until the velocity dropped down to 0, and then the velocity would be negative, and you continue on in that path. So what do these values mean? Well, the values of the initial condition are the reality of initial position and initial velocity. One of the hard things for people to kind of wrap their head around when you're looking at the phase plane, and that's what this graph is here, the phase plane is not reality in any stretch, right? This plane doesn't represent what the mass is doing. It represents the position of the mass at any time and its corresponding velocity. So you will never see your mass on a spring move like this. It's not going to look like a circle. It's only going to behave this way on the phase plane. So you have to be able to interpret what's going on with the phase plane. So we'll take a look at the next page here. So at the top of the next page, you can see we've got a graph. And of course, it's always good to kind of read the axes of your graph to figure out what's going on. This is position versus time. And you can see right here, there's my initial value. There's my y0 equals 1. So that corresponds with what I saw on the previous graph, what we were doing on the previous graph, with an initial position of 1. And because it's moving upwards like this, the position is getting further away. That's telling us it must have a positive velocity. You can actually read this graph and see the slope of this line right here, of this curve right here. The slope of this graph is the velocity. So here it's a positive slope. That means we've got a positive initial velocity. So v0 is greater than 0. You can tell just by looking at the shape of the curve. But you can also see that the velocity slows down. It winds up being 0. You have a maximum point right there where your velocity reaches 0 at some time value, and then the velocity starts to become negative, and down here the position's negative. So like we were in Calc 1, we can read this graph and get a sense of what's going on. So you'll notice I also added a title for this one, and I actually said b equals 1, and I shouldn't have said that because technically we haven't included the b yet. The b is for the damping coefficient. We'll get to him in a second. Speaking of which, down here on the bottom, we're going to make things a little bit more interesting. We're going to add what's called a damping coefficient. We are literally going to add friction to this. So the damping force, and this is true whenever you're talking about any kind of situation where there's damping, that's really just a force that's fighting the velocity. And by fighting, hold on, let me write here. By fighting, I mean it's always oppositional to. So if you have a positive velocity, then that means you're going to have a negative force. If you have a negative velocity, that means you're going to have a positive force. So it's always fighting against whatever the direction of the velocity is. It always fights, it always opposes the motion. So the way we're going to do this is we're going to start constructing from kind of scratch here, and we're going to say let the net force on an object equal its mass times its acceleration. That's Newton's second law. So that's a good place to start. And really what that's saying is that the sum of all the forces acting on the mass is equal to its mass times its acceleration. So in the previous example, we just said, oh, there was only one force. It's the restorative force, whatever that happens to be. And so we would have said, oh, that's just the force due to the spring, the restorative force due to the spring. But now what we're going to do is we're going to include another force in this mix, but it's going to fight against, right? And so in this case, we're going to have another force that's also going to be fighting things, and that's the damping force. Now, for different situations, damping can be caused by, could be air resistance causes damping. It could be caused by the friction against the table. So if you have an object kind of running along a surface, it creates friction with that surface. Another source of damping is what's called a dashpot. And I'll see if I can find an example to show you here. So here I found an example of a dashpot. This is kind of a cutaway view of a cylinder that has some kind of a mass in the middle attached to some kind of like a plunger, right? You can think of it as like a piston. And so as you lift up or push down on this, the mass is going to move through the liquid. This could also be a propeller, right? And so if you try to rotate this, rotate this propeller, it's going to get slowed down by the liquid, whatever is in there. So the fancy word for this in engineering is a dashpot, right? This is just a fancy way of saying something that is opposing motion and slowing down motion. So back to the equation, we can actually go ahead and write down what we know about the spring. It's negative k times y. That's the Hooke's law. And then in terms of the damping force, we know that it's fighting the velocity. So it really just depends on how big the velocity is. So what we're going to do is we're going to throw, because this is going to be fighting things, so it's going to be negative, we're going to throw in a coefficient. We'll call it b for the sake of argument. And then we're going to make it times the velocity, the dy dt. We're basically saying whatever the velocity is, we're going to multiply it by this damping coefficient. Right? And so what we're saying here, the argument that we're making here is that damping is proportional to the velocity and opposite in direction. And you can tell it's opposite in direction because, of course, I should include the negative there, right? So it's in opposite direction of the velocity, so it's always going to be fighting whatever the velocity is doing. If the velocity is positive, then this will be a negative force. If the velocity is negative, then this will be a positive force. Okay, so now that we have that, we can actually go ahead and kind of simplify things a little bit and say, remember, mass times acceleration on the other side. That's mass times the second derivative of position with respect to time. And then on this side, we've got minus k times y. And then this is minus b times dy dt. Now you can call this y double prime and this y prime if you like. I'm just trying to remember that these are actual derivatives with respect to time. And so what we have here is a second order differential equation. And so I'm going to clean this up in a second, but I want you to see that this is a second order differential equation. There is two derivatives. One of them is a second derivative and one of them is a first derivative. And so if you write it this way, you can say mass times y double prime equals minus k times y minus b times y prime. That might be a little bit easier, more familiar. Just remember that y prime is equal to dv dt and, oh, sorry, dy dt, whoops, and y double prime is the same thing as dv dt. That's the derivative of velocity with respect to time, or the second derivative of position. And so we can use this idea to manipulate and come up with literally a system of first order differential equations similar to what we did before. So we're going to make a system of first order DEs. And so we're going to do that here by taking this equation right here, knowing that y double prime is dv dt, and we're going to use and manipulate this equation by taking, what was I saying? Oh yeah, this thing, and substituting it in and manipulating it a little bit. So our two equations are going to turn out to be, one of them is dy dt is just velocity. That's the first one that's kind of obvious, right? That's dy dt equals velocity right here. And the other equation is going to come from manipulating this. So if I substitute dv dt in for this, I can manipulate it around a little bit and say dv dt equals, divide both sides by m, and we have negative k over m times y minus b over m times v. And so this system, these two systems are 100%, this system right here is 100% interchangeable with that second order differential equation. They are truly 100% the same thing because of this side relation that we have, that y prime is v and y double prime is dv dt. So we're going to use this to our advantage, and we recognize that these values that are stuck in the equation, these values of k and m and b, are all just parameters. That means that we can make them whatever we want. They're just numbers, right? The k relates to the how stretchy the spring is. The mass is how much mass is on the spring, and b is how much friction there is basically acting on this. So on the next page, we're actually going to take some time to visualize this with Maple and then write down what we notice. So we'll do that in the next video.